Equation for differential is exactly the type.
Thank you very much. First of all, I would like to thank the organizers for giving me the opportunity to speak at this meeting. I will talk about the Martingdale solution to the non-Newtonian fluids, which is also known as the second grade fluids. It is basically an incompressible fluid, and its tensor matrix is given by this polynomial of degree 2 as a function of the first and the second Rivlin-Erikson tensor. We can find more information about the second grade fluid in these two papers of, not two papers, but this is a book, and this one is a paper about the physical of the second grade fluids. Those fluids describes a large class of, yeah?
There's something wrong with the microphone.
This side. It's okay now? Okay. They have a lot of, they describe a large class of non-Newtonian fluids, mostly industrial fluids, and also they are connected to the turbulence theory as this work of Rivlin revealed. And later on, Foyas and his colleagues somehow rediscovered this relation to the turbulence theory. In this slide, we will try to describe how do we get the motion of the fluids. So if this is the dynamical equation of a fluid with tensor T. So if you take the divergence of the tensor that we gave here, then you'll end up with this equation, assuming that the velocity is 0 on the boundary. What we want to do in this talk is to replace this force F by some random perturbation, which is described by this term. In this term, the eta tilde is a compensated Poisson random measure defined on this space. Right here, the omega ftp is a filtered probability space, and side with this sigma field is a complete separable metric space, and we assume that we are given a sigma finite positive measure on that space. In the deterministic case, the equation have been studied extensively, but we cite only some references which are relevant to our study. The first work in the second grade fluids was this paper of Suranescu and Elassen. They proved the global existence of weak solution in 2D, and later on Suranescu and Giraud extended their result to the 3D case by obtaining some global existence of weak solution with small data. Bernard studied a more general, more complicated equation, and he could obtain also the global existence of weak solution with small data in the three-dimensional case. In the stochastic case, Sango and myself proved the global weak martingale for the Gaussian noise. But in this talk, we want to see if those global existence of martingale solutions still hold if we replace the noise by Poisson random measure noise. And the sketch of the proof of this result is the object of this talk. To set up our study, we will introduce this function. The H and the V is the well-known spaces in the Navier-Stokes. Due to the non-linearity, we have to introduce this space W, which is a subspace of V, and every element of W must satisfy this condition. On V, we assume that we have this scalar product, which is equivalent to the gradient null. And on W, we consider this scalar product, which is equivalent to the usual H3 norm. We also note that W is compact in V. And throughout this talk, we assume that we identified V with HDL, and we consider this triple of this chain of embedding, which is in fact compact and dense. And also we introduce this space, the space of basically a counting measure on Z times 0t. And we would like also to introduce some operator that we will need at the last part of the talk. This operator A, and we want to introduce an operator which is very similar to the bilinear form in the Navier-Stokes. So we consider this formula, and we can prove that this trilinear form satisfies this inequality, and so that we can infer the existence of a bilinear form B satisfying this this formula 6 and satisfying these inequalities. We will not really use them during most of the part of the talk, but they seems to be useful at the end. And we also introduce this notation, where here the R bold is just the Stokes operator. So we wanted to study the existence of martingale solutions. So what kind of martingale solution we are interested in? So it's basically the same definition as Professor Motil's definition. We look for a system like this, where WF, F bar, P bar is a complete filtered probability space. Eta star is a time homogeneous Poisson random measure. U is a F progressively measurable, satisfying this estimate. U is CAD lag. And you satisfy the equation 2 in the sense of, in the weak sense, PDEs. That is to say, it satisfies this formula. So before we state our main result, we want to state the main hypothesis used for the proof. So we assume that this function sigma, the coefficient of the noise, is continuation in the variable t and u, and we also assume that it satisfies this graph. So this is our main result. We assume that psi is a complete separable metric space on which is defined as sigma finite measure mu. We assume the initial condition is in W, and we assume also that the previous condition holds. Then there exists a Martingale solution to 2 in the sense of definition 2. The proof is very similar to what Professor Motil did. We used the Galerkin method by following the method of Sioranescu and LSN, and we use some compactness method also by following the spirit of Métivier and Brezhnev and Rosenblatt. The main difficulty here is that we cannot expect any smoothing from the non-linear term. Roughly speaking, it is dominated by the non-linear term, which is of degree 3. So in some sense, it's not a smoothing term, but rather a damping term. But we can overcome this difficulty if we choose a special basis for our Galerkin like this. So we consider a orthogonal basis of W, which are solution of the spectral problem. And we should note that the elements of the basis are in H4 if the boundary of the domain is of class C3. And then we require that the Galerkin approximation satisfy this equation. And the next step is to derive some a priori estimate, which is tested in this lemma. So this is the main difficult part of the proof. So we would like to talk a little bit about it. So to prove this lemma, we have to follow 2 steps. First, we need to prove that is in this space involving, UM satisfy 13, but we replace first W by V. And to do that, we introduce again the Stokes operator and transform the Galerkin approximation 12 to this one. So what changed is this term, so that we can transform this scalar product in L2 to a scalar product in V. If you don't do that, then you will not get a uniform a priori estimate. So, and then after doing that, you just use Ito formula, and you can prove that in fact this is not correct. There should be a mathematical expectation here satisfy, and this process satisfy the Grunwald lemma. The second step is to finish the proof of 13, and we have to transform again 12 into this one. Actually, what we should do is to transform the scalar product V into a scalar product in W, but you'll do that if you multiply this formula by lambda E and use the definition of our special basis. So why we need to do that? The reason is quite simple. We want to estimate we want to apply the curl operator to this equation, so that we get the norm of this guy in L2. So, and you see that if you transform this this quantity by multiplying by lambda, you get a scalar product in W, and you just again apply the Ito formula with some, with the same argument as before, and you can prove this estimate. The estimate in 13, sorry. And having that done that, we want to prove the tightness of this couple, which is nothing but the solution of the Galerkin and this new sequence, which is defined by this one, which is basically a stationary sequence. We want to prove that this couple is tight on this space. To do that, we exploit our a priori estimates to prove that for any epsilon positive, we can find a compact in this space, such that we have this. The comma should be here, sorry. And then secondly, we prove that there exists a constant C positive, such that this estimate holds. And those two facts will enable us to prove that UM is tight on this space, the space of Cadillac function taking values in W star. And the tightness of UM on L20 TV follows from some arguments from Métivier's book. And the family of laws of the Poisson random measure is tight on this space. So we can conclude easily that the family of laws of the couple is tight on calligraph S. No. So we can proceed now to the proof, and you use Prokhorov theorem. Since the family of law is tight on this space, which is Pauli space, then we can extract a subsequence and we can find a probability measure defined on S, such that the law of the couple will convert weakly in to mu star. And after that, we use Corrode-Medin theorem to find a new object bar, eta m bar, u, eta star, such that the law of those two objects coincide, and the law of u and eta star is equal to the mu star. And also we have this this convergence, strong convergence, and also we have this identity, which is proved in Brezhnev and Rosenblatt. Now we construct filtration, which is generated by eta star sorry, 7. Yes. Rosenblatt proved that they actually coincide.
It's constant.
Yeah.
We take if we lose a Gaussian random measure, we don't have any Martingale representation. So we take it from the limit and take all the time the same one.
So now we construct this filtration, which is generated by eta star, and u, and we prove this this lemma, which allow us to define everything in the next slide.